So I think we'll start the session for today. So good evening to all the participants, and welcome to this live interaction session.
Good evening.
Yes, good evening. And this course is brought to you by NPTEL. The course is called Advanced Reinforced Concrete Design, and the course is instructed by Professor Surya Prakash of IIT Hyderabad. And today we are in the 12th and the concluding live interaction session. So it was supposed to happen on Saturday, but I was not feeling well, which is why we had to postpone this session. And in today's session we are going to be dealing with the analysis and design of two-way slabs. So this session is brought to you by presented by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. So I think without any further ado, we can start the session. But before starting, I will just give a brief outline as to what we have covered in the lecture this week, in this week's lecture by Surya Prakash sir. So essentially we are going to we have studied the analysis and design of two-way slabs. So in the first part of the module 10, we looked into the overview and the flexural behavior of the slabs, and in module 10.2 we looked into the direct design method, and in module 10.3 we looked into the equivalent frame method. So in today's class I have selected one problem on the Codal coefficient method, which is as per IS 456, and one problem is based on the direct design method. And because of the shortage of time, I have not taken up any problem on the equivalent frame method. I think I have planned around 14 to 15 questions. So without any delay, we can get started with today's session. So the first question is, identify the incorrect statements on the dimensions, behavior and design of reinforced concrete slabs. So there are 5 options. Kindly take 1 or 2 minutes and let me know what are the incorrect options.
The screen is not sharing.
Oh, I'm sorry. Okay, I hope that it is visible now.
Yes, sir.
Yes, yeah. So please take 1 or 2 minutes and let me know what are the incorrect options.
A, B, and D are incorrect, sir.
Okay, thank you for the response. So yes, I think that is the correct answer. And yes, so one-way slab is one where the ratio of longer to the shorter side is at least equal to 2 or greater than 2, and one-way slab deflects in the shorter direction, which is why in a one-way slab the reinforcement is the main reinforcement is provided along the short direction only, and yes, in a two-way slab, the ratio of the longer side to the shorter side is less than 2, which is why it bends along both the directions in order to develop a dish-like form, and hence the main reinforcement is required along both the directions, along both the shorter as well as the longer directions. So moving on, yes, so we will dive straight away into the numericals now. So I have shown a floor slab system of a multi-story building here, and the slabs are supported by 230 mm thick masonry walls, and if we consider 150 mm thick slabs and a floor finish load of 1 kPa and a live load of 4 kPa, so determine the factored moments per meter length along the shorter span of the interior panel S4. So the question here is, for this interior panel, what would be the factored moment along the shorter span? Okay, so kindly take 2 minutes and let me know what would be the right answer. And please utilize all the data that is being provided. So the clear cover is 20 mm, and we are considering a reinforcing steel of 8 mm along both the directions, along both the shorter span as well as the longer span. Okay, I'm going to start Do we have an answer, or shall I start solving the problem?
Yes.
Hello?
Sir, you can start, sir. I am also doing.
Okay, okay,
You can
okay.
start.
Yeah, thank you. Yes, so I'll start off with drawing a sketch of the interior slab over here. Okay. Um, I'm sorry, you have to bear with my poor drawing for today. So here we have the clear span as 4000 millimeter, and along the longer direction the clear span is 5000.
Sir, LOI and LX, sir, clear span or effective span, sir?
I'm sorry, sir, what did you say?
Length of short span, long span means it is a
Yes.
clear span. Na? It is clear span.
You mean for while considering in this table?
Yeah.
No, this will be effective span.
Center to center of pulse.
Yes, sir. Not exactly, because like there is one more clause that, like the effective span, L effective, L effective is equal to L clear plus D. So
Effective depth of slab.
yeah, effective depth. So this and the center to center, whichever is less, you have to take that value. So
Okay. Sir. Okay.
yeah. Okay, thank you. And okay, let me start with calculating the I'll write here because of the paucity of space. So I'll start with W self weight. W self weight is I've given the thickness of the slab as 150 mm, 25 into 0.15 is 3.75 kPa. Okay, and the factored load would be 1.5 times 3.75 plus 1 kPa for the floor finishes. And what is the live load? Live load is 4. So when we simplify, we get WU is equal to 13.125 kPa. Further, as the participant rightly mentioned, once we have this value, we need to find out the effective span. Right. So we have first we will find out, even in a two-way slab, what happens is the shorter span becomes the main direction of bending. Okay, so I'm going to take it as dx, that is the shorter span. So dx is given by, I'll write here dy also. This is the effective depth along the longer span. This would be 150 minus 20, which is the clear cover, minus 8 by 2. So this will give me 126 millimeter. Now the effective depth along the longer direction, that would be 126 minus 8. So that would be 118 millimeter. Correspondingly, we have Lx is equal to the clear span plus the d value, that would be 4.126 meter, and Ly is equal to 5.118 meter. So this is these values of the effective span, they are less than the center to center distance between the supports. So these will be the effective span considered for the calculations. Okay, so now we need to find out the ratio of the longer span to the shorter span, right? So we have for Ly by Lx, because of the shortage of space, I'll write here Ly by Lx. So that simplifies into 1.240. Okay, so this 1.240 value, this is going to help us in finding out the bending moment coefficients. Okay, since we have taken the interior panel corresponding to different values of Ly by Lx, we can determine the bending moment coefficients. Okay, so do we have space? Okay, I think we need to manage somewhere here only. Okay, so for this I am getting we have to interpolate between these two values, 1.2 and 1.3, for the shorter span coefficients. I am going to consider that as alpha x negative and alpha x positive. Okay, so the first value would be alpha x negative, the second one would be alpha x positive. So I got a value of 0.0446. Okay, so if you see here between 1.2 and 1.3, I'm getting a value of 0.0446. okay, so that is how we need to interpolate. And similarly for alpha x positive also, it has to be between these two values. I'm getting a value of 0 3 3 6. Okay, so now I will write the equation, and you can help me to simplify that and obtain the right answer. So along the shorter direction, the factored moment mux positive and mux negative would be alpha x positive wu lx square. Okay, and we have mux negative is alpha x negative wu lx square. Okay, so this is where we are obtaining these from the annexure D of the IS code. So when we substitute these values, alpha x positive 0.0336 into wu is 13.125 and lx is 4.126. when we simplify them, we obtain a value of 7.51 kilonewton meter per 1 meter of the slab width. Okay, similarly for mux negative, when we substitute alpha x negative as 0.0446, wu as 13.125 and lx is 4.126, we obtain the value as 9.97 kilonewton meter. Okay, so this is the right answer. So yeah, as we can see, option C is the right answer. Okay, so we have completed the second question. So the third one, the third question is also based on the same floor slab system. So yeah, here is the problem. In the earlier question, we determined the factored moments along the shorter span. Now in this question, it is required to determine the factored moments along the longer span. Okay, so kindly take 2 minutes and let me know what is the right answer. I will start solving the problem with you. So we have the ratio of the longer span to shorter span, Ly by Lx is equal to 1.240. Correspondingly, we need to obtain the values of alpha y positive and alpha y negative. Finally, the factored moments would be muy positive is alpha y w.
Answer is D, 5.4 and 7.2.
Okay, thank you for the response. Yeah, so I think we can go straight away to the solution, and the answer is absolutely right. So let us look into the table in Annex D once again. So for the shorter span, we need to obtain the bending moment coefficients by interpolation, but for the longer span, it is fixed. So irrespective of the ratio of Ly by Lx, we have the alpha y negative. Alpha y negative is 0.032 and alpha y positive is 0.024. Okay, so positive is 0.024, and alpha y negative is 0.032. Okay, so even I would like to mention that even when you are determining the factored moment along the longer span, we still have to consider the effective length along the shorter direction. So when we simplify this, I am getting MUY positive is equal to 5.36 kilonewton meter, and MUY negative is 7.15 kilonewton meter. Okay. So thanks for the response. We can move ahead to the next problem. Yes, so here is a conceptual question on the direct design method. Kindly take 1 minute and let me know what would be the right answer.
A and C are correct, sir.
Okay, thank you for the response. Yeah, so let's not delay any further, and yes, absolutely, A and C are the right options, because it is an empirical method of distributing moments between the slab and the beam sections, and then we will design the slab and beam accordingly depending on the moment that is acting on these members. And option B is incorrect because it tries to fulfill the criteria for the limit state of collapse and the limit state of serviceability simultaneously. And option C is correct because it involves a single cycle moment distribution analysis. On the other hand, the equivalent frame method, it involves multiple iterations of the moment distribution. And option D is incorrect because it one of the limitations is that it cannot be applied to floor slab systems of asymmetrical dimensions and asymmetric loading patterns. Okay, so I have highlighted.
Sir, coefficient method also empirical method, no? First one also.
Yes, sir. That is also empirical method. Yeah.
Coefficient method. Both for both it is empirical method.
Yes, yeah. Because we are, obtaining the coefficients based on, our experience. So,
Okay.
yeah. Equivalent frame method is more closer to the analysis actually, because we are actually performing the analysis based on the cross section of the columns, the slabs, and so on. And yes, as you pointed out, we can classify both the Codel coefficient and the direct design method as empirical methods. Yeah, so we will start with another problem. So yeah, I think we are starting with this numerical on the direct design method now. So kindly take 2 minutes and let me know what would be the right answer. So we need to determine the beam stiffness parameter alpha b. Okay, so I will start solving with you, then I will provide you hints as we go along. Okay, so what we have here is a floor slab system, and it is required for us to design the exterior slab panel, that is S1, and this consists of 4 supporting beams. So we will start with this first beam, and then we need to determine the beam stiffness parameter alpha b. Okay, so I will give you a hint so that we can get started with this. So this beam stiffness parameter, as you might remember from the lecture, is alpha b is nothing but the ratio of the moment of inertia of the beam to the slab. Okay, so if you know the solution, please go ahead, or else we can start we'll start solving the problem together. Okay, so we need to find out firstly the moment of inertia of the beam. So this is kind of an inverted L beam. Okay, so whenever we are considering the slab action, we need to take into account we need to consider the beam as a flanged beam. Okay, so this slab width is 180, and so this leaves us with the overall depth of the beam is 550. So essentially this is basically the engineering mechanics part, where we have studied how to locate the neutral axis for a given cross section and how to determine the moment of inertia about the centroidal axis, right? And the width of the beam is 400 millimeter. Okay, and this we have seen in one of the lecture slides, that this particular value has to be how much? BW plus DW. It has to be equal to the width of the web plus depth of the web. So that would be 400 plus 370. That will give us 770. Okay. So I'll tell you where I got. So you have to locate the centroidal axis. Y bar is equal to summation of AI into YI divided by the total area. Okay, for which I got the centroidal axis below the slab, I'll write it here so that it is more clearly visible. Okay, so this is 232 and 318. So I got Y bar as how much? 232 millimeter. Okay, so now we need to determine the moment of inertia about the centroidal axis. Okay, so what we need to do is we have to divide this flange section into two parts, take the moment of inertia. Yeah, Ix is equal to I plus A into h square. Okay, so I got a value of, let me write it as IB in order to maintain the uniformity of the notations. To the power 9 millimeter power 4. So this is how you find out IB. So I would just like to pause and ask if there is any doubt. Is there any doubt, sir?
Actually,
Yeah,
Vegas is coming 317, sir.
317, huh?
And IB is matching 7 point plus.
Okay, IB is correct.
Uh,
Okay. I mean, just I would suggest you to check it once again, because Sir, from here it is 318 from below. Is there any chance that you have interchanged them?
Uh-huh.
From below it is 318.
Yeah. From below I was taken actually.
Okay, okay, okay. That's
In the
nice.
lecture it is taken from below. Okay, thank you.
Okay, okay. Yeah, yeah. Thank you for the clarification. So we have obtained the value of IB. Now we need to obtain the value of IS.
Actually, it has to take from top, no, sir?
Yeah, yeah. Actually, it doesn't make a difference, sir. But
No, if
yeah, if
any
it
question
is,
they will ask, then we have to refer from top only, no?
yeah, yeah, yeah. Because it basically depends on how you were taught when you were. So I have the practice of taking the from top only. So, yeah. Okay. After this, you have to determine the
But actually in lecture it is taken bottom only, sir.
yeah, yeah. Okay, sir.
Lecture
That
notes.
that is not an issue because
Okay, okay.
ultimately we want this IB value.
Okay, sir.
So no issue with that, sir. Yeah. Excuse me.
I'm getting 3.68, sir, actually.
Okay, so we can move ahead. So we got the value of IBS 7.475 into 10 to the power 9, and when we consider the slab, okay, so since it is an exterior beam, we need to consider only half of it. Okay, so I will show you. So when we are considering the slab dimensions, this width would be 3200, and the depth would be 180. So IS would be okay. Sir, I hope you followed this
Uh,
method.
yes, right. That's 4.8. Yeah.
Yeah, yeah. So we have to be a little careful while we are considering the exterior slab.
Yeah.
5 into 10 to the power 9 mm power 4. Okay. And we have alpha b is equal to IB by IS. So alpha b is equal to 4.807.
Yeah. Yes.
Yeah. Okay. Thank you for your response and solving the problem. So option A is the right answer. So for this floor slab system design according to the direct design method, what I have done is for the exterior panel, I have divided the problem and once we have all the constituent results such as alpha b for each of them, then we will go ahead and tackle the problem together as a whole. Okay. Okay, so we can move on to the next segment of the problem. So for the same exterior panel S1, we have to determine the alpha b parameter along the edges A2 B2 and A3 B3, that is A2 B2 and A3 B3. Okay, so please note that it is going to be continuous along this direction. Okay, you may please start solving the problem when I will start solving now. And this the width of the flange would be BW plus 2DW, BW plus 2DW. That is 400 plus 2 times of 370. That gives me a value of 1140 mm. 1140 mm. Okay, so for this we need to determine the location of the neutral axis. Okay, okay. So for this I section, for this T beam, I am able to get a value of 205.2. Depth of neutral axis from the compression edge and 344.8. Okay, and correspondingly, what is the value of IB? So the value of IB I'm getting it as 8.745 into 10 to the power 9 mm power 4. Okay, now we need to consider the slab. So the cross section is not to scale. Okay. So we have slab that is 7500. So for this beam we need to consider along this direction. Okay, so for this for the beam along A2 A3 we consider the slab in this direction, and for the beam that is along A2 B2 we need to consider the slab along this direction. Okay, so that is 7500 and 180 thickness. Okay, we get the value of is is equal to
3.6.
yes yes 3.645.
And alpha is 2.4.
Okay, 645 into 10 to the power 9. Okay, so we have alpha b, let me write it here. Alpha b is equal to IB by IS. Taking the ratio I got a value of 2.4, right? So option C is the right answer. I hope that you're getting the same answer, sir.
Yes, sir.
Okay, thank you for the response. We can move ahead. Option C is the right answer. Now we have found out the alpha b parameter for this beam and for these two beams. Now we need to find out the alpha b parameter for the beam along B2 B3 edge, B2 and B3. Okay, we can start solving the problem now. Okay, so we have the
Answer is 3, sir. Answer is C.
okay, yeah, thank you for the response. So yeah, as you pointed out, since the cross section is same, we already have the value of IB. We only need to find out the
Yes,
value
sir.
of IS. So I will
Yes.
just write down the sketch, for the sake of the completeness. For those who are watching later the recording, just so that it makes sense for them, I will write down. So this would be 400, and this depth of the web is 370. Okay, and yes, the width of the flanges BW plus 2 into DW, so that gives me a value of 1140. It is exactly the same as the previous one, and the width of this The thickness of the slab is 180 mm. Okay, it is 180, and yeah, I'll draw the slab also here so that we can straight away go for the calculations. So this is just a discontinuity symbol to show that the length is much more higher when compared to the thickness. So the thickness is 180, and what about the length? We are considering this particular beam. So the width of the beam is 6000 millimeter. Okay, so I'll take a different color now, purple. Okay, so IB is same as the previous problem. IB is 8.745 into 10 to the power 9 mm power 4, and IS is equal to 2.916 into 10 to the power 9 mm power 4. Okay, further, alpha B, as we know, is the ratio of IB to IS, and the answer is 3.2. So it is absolutely right. So we will move on to the next part of the question. Now we need to determine the moment of inertia of the beam slab member along the shorter span of exterior panel S1. Okay, so I will just draw a sketch for you so that we know exactly what we need to find out. Okay, so we need to find out, we need to consider this beam as a beam slab member, and we need to determine the moment of inertia, or what is called as ISB. ISB. This will help us in our calculation of the moments later on. Okay, so I will draw the sketch. I'll try to draw it neatly so that okay, so the width of this slab is 7500, the center to center distance, and we have the beam which is at the center. Yeah, so the width would be 400 and this depth is 370. of the web. So we need to consider this entire slab and the beam as one composite section, and then we need to locate the neutral axis. Then we need to determine the value of ISB. Okay, so kindly take 1 minute and let me know what is the right answer. And this is 180 mm. We know that this is 180. So do we have an answer?
Sir, 15.4.
Okay, wonderful. That is the absolute right answer. So when I calculate the neutral axis, this particular distance from the top fiber, I obtained the value as 117.2. Okay, 117.2 millimeter, and from the bottom just 550 minus 117.2, that is 432.8. 432.8. Okay, and taking the moment of inertia about this centroidal axis, ISP value is 15.42 into 10 to the power 9 mm power 4. So option B is absolutely right. Yes. Okay, I think I need to write it clearly here. 117.2. Okay. Okay, now we have the alpha B data for all of the beams that is supporting exterior panel S1, and we have the floor to floor height as 3.5 meter. The column dimensions are given 400 by 400 mm. We know the beam dimensions as well. Now we need to determine the slab thickness, the minimum slab thickness that is required for the exterior slab S1 for deflection control as per the Canadian code provisions. Okay.
Sir, 195 on point.
195 is it? Okay.
Yeah.
Okay. Thanks for the response. But sir, your calculations are right, but there is one catch actually. So this, we have the value of alpha bm. So this is the mean value of all the alpha b. So this has to be limited to a value of 2.0. So just try to substitute that value and see what is.
Sir, I consider, sir, I consider them.
Okay. So we can see that. Because I am getting a different answer. We'll see. We'll solve the problem together and we'll see what is the right answer. Okay, so first we'll find out the value of alpha bm. Okay, so start with alpha bm is equal to 1 by 4 into, we will start adding the alpha b value for each beam, 4.807 plus 2 into 2.4 plus 3.0. So got a value of 3.15, but it should not be greater than 2.0. So alpha bm is 2.0. As per the Canadian code, D, I'll take a different color. D should be greater than or equal to ln, okay, ln into 0.6 plus fy by 1000 plus fy by 1000. Okay.
Yeah, I was taken 500, sir. Okay.
Okay. yeah. Divided by 30 plus 4 into beta into alpha bm.
That became 180, sir.
Okay, yes. Okay, please excuse me for 1 minute. Okay, sorry about that. We can continue solving the problem here. Okay, so yeah, we can start plugging the values here. So here ln is nothing but the clear span along the transverse direction. Okay, so the clear span 7.5 minus 400, so that is 7100 mm, 00 mm, right? And fy is how much? 415 MPa. Okay, and beta is the ratio of the longer span to shorter span, and both of them needs to be the clear span values. Okay, so that is 7100 by 5600, so that is equal to 1.268. okay, and alpha bm is 2.0. so we'll plug all these values in the equation. D should be greater than equal to 7100 into 0.6 plus 0.415 divided by 30 plus 4 into 1.268 into 2.0. Okay, so when we simplify that, we get D is equal to 179.52. So in order to ensure the deflection control check as per the Canadian code, we need to provide a minimum overall slab thickness of 180 millimeter. So option C is the right answer. Okay. So this is the next part of the question. So we need to determine the total design static moment and the longitudinal positive and negative design moments for the panel S2. Okay, so we need to consider the design moments for the interior panel S2. Okay, kindly take 2 minutes and let me know what is the right answer.
The answer is B. The answer is B. B for Bombay.
Yeah, thank you for the response. Yeah, we can start solving the problem actually. Okay, so for the interior panel S2, first we need to determine the design static moment. Okay, so prior to that, let us determine the loading, that is factored loading on the slab, that is WU. Okay, WU is equal to, first we need to consider self weight, 25 into 0.18, okay, plus 5 plus 1 multiply by 1.5. Okay, which is 15.75 kilonewton per meter square. 15.75 kPa. Okay, and now we have the static design moment m naught. Okay, I'll write it here so that we can or else I'll write it here, I think, because there might be space in the next slide also. M naught is equal to WU L2 into ln square divided by 8. Okay, so okay, yeah, we have space over here, so we have m naught. Okay, m naught is equal to 15.75 into L2. L2 is basically the distance in the transverse direction. It is 7.5. Okay, 7.5 into ln is the clear span in the shorter direction, that is 5.6 meter. 5.6 square divided by 8. So that gives us a value of 563.05, sorry, 463.05 kilonewton meter. Okay, now how do you determine the longitudinal positive and negative design moment? So these are simply given by the positive moment is, I will perhaps take a different color now. Okay, so for the interior panel, so this is the distribution that you can expect. At the ends it is 0.65 m naught, and at the center it is 0.35. Okay, so we have let me call it as MUX negative and MUX positive, that is 0.65 m naught and 0.35 m naught. Okay, this is equal to 300.98 kilonewton meter, and this would be 162.07 kilonewton meter. Okay, so 463, 162 and 300. So option B is the right answer. Now for the floor slab system that is given in the question 10, and from the total design static moment calculated, determine the positive design moment in the span and negative design moment at the exterior and interior supports for the panel S1. Okay,
All options are given same, sir.
Oh, okay, okay. I think I have.
It is correct, sir.
Yeah, yeah, yeah. I think I. Yeah, please excuse me for a minute. I think I forgot to um, take the actual this thing. I guess I think I had prepared the final presentation, but I think yeah. Please give me 1 minute. Let me figure out what exactly happened. Please take a break of 5 minutes. We will start at 8:40.
Okay, sir. Okay.
Yeah, yeah. Thank you. Hello.
Yes, sir.
Yeah. So I'm back. We can continue. So sorry for that. I had kept the completed presentation in my office PC. So yeah. So we were in question 11. We have another 4 questions for today. So kindly take 2 minutes and let me know what is the right answer. So for the exterior span, we have the distribution of moments in the longitudinal direction in this manner. Yeah, I'll okay. Here we have 0.65 m naught by q. Here we have 0.75 minus 0.1 by q into m naught, and at the middle we have 0.63 minus 0.28 by q into m naught. So we are seeing this new term called q. So what does q exactly mean or represent? So q here, I'll better write it here only. So q is equal to, this parameter is given by 1 plus 1 by alpha c, okay, and here alpha c is equal to summation of kc by ksb. Okay, so we need to consider the exterior an exterior point such as this, exterior column such as this. So we have 2 columns that are meeting, that is one above the level considered and one below, that is 4 EIC by LC into 2, we are considering 2 columns, divided by 4 EISB by L1. Okay, L1 is the L1 is this direction, okay, the primary bending direction. Okay, so here we can cancel out 4e and 4e. Okay, so this simplifies into 2 IC L1 divided by ISB into LC. So upon simplifying, I got a value of 0.4 4743. Sir, I hope you are getting the similar answer. Correspondingly, Q will be 3.108. So we'll just plug it over here, and let me call it as you can simply call it as M1, M2 and M3. Okay, this particular value, I'll take a different color and let's start solving. Okay, here M1, M2 and M3. M1, M2, this is M3. Okay, just simplify, and so for this I got a value of 96.84 kilonewton meter. That is the negative moment at the exterior support, and the positive bending moment at the midspan, this particular value, that is M2, I got it as 250.01 kilonewton meter, and the negative bending moment at the interior support, that is M3, that I got equal to 332.39 kilonewton meter. Okay, so the positive design moment in the span, that is 250. Okay, 250, and the exterior support.
So your voice not coming?
My voice is not coming. Hello, am I audible? Hello, I hope I'm audible now. Okay, I think I'll just leave the meeting and I'll join once again.
Yes, sir.
Hello.
Now it is.
Yeah.
No.
Okay, thank you. Okay, so we will continue with the problem. So I got the value of the positive design moment in the span, that is 250, and the moment at the negative moment at the exterior support is 97, negative moment at the interior support is 332 kilonewton meter. Okay, so moving on, so we have determined essentially the distribution of the moments along the longitudinal direction. So now we need to determine the distribution along the transverse direction. So for the distribution of moments in the transverse direction between the beams and slabs, what are the widths of the beam and slab to be considered for panels S1, S2 and S3? So kindly take 1 minute and let me know what is the right answer.
Sir, 1140
Yeah, thank you for the response. So it is quite obvious. Yeah, option D is absolutely right, because if you take the composite action of the beam and the slab, so we need to consider the T beam. So the width of the beam would be BF is equal to BW plus 2 into DW, that is 400. Sir, can you please mute your speakerphone? 7500 minus 1140, this gives us a value of 6360 mm. Now in the next problem we are going to look at the distribution of the moments between the beam and the slab in the transverse direction. Okay, so we can actually solve the problem together. Okay, so we need to determine how this distribution is taking place. Okay, so I will just start solving the problem. Okay, so here we have the panel S1, we have the panel S2, and then we have the panel S3. Okay, so both the panels S1 and S3 are exterior and S2 is interior, and basically we are considering a symmetrical section because whatever analysis and analysis results is obtained over here is applicable for the mirror image also. Okay, so we have reported only one side of the problem. Okay, so as I was mentioning in the previous slide, so here we have the beam segment we have. Okay, and here the slab. So here 3180 is nothing but 6360 by 2, and here it is again 6360 by 2. Okay, And let us see how we will proceed and distribute the moments between the beam and the slab. Okay, take a different color. So the proportion of the moment that has to be resisted by the beam, okay, that is given by the percentage of moment that is resisted by the beam is given by alpha b1 divided by 1 plus L2 by L1 whole square. Okay, but here the criteria is that alpha b1, the stiffness parameter, should not be greater than 1.0. okay, so though we get very high values for this problem, we got values which are exceeding 3 and 4, but still we need to limit ourselves to this value of 1 only. Okay, so this gives us a value of 1.0 divided by,
Sir, alpha B1 means any beam, yes, sir.
yes sir. So it essentially means this beam actually. Okay,
Center.
yeah.
Okay,
So
okay.
where we are
Okay.
distributing. Okay, so if we go back, I think the actual alpha
Sir,
value.
sir, actually,
Yeah,
pardon me, sir.
yes please.
Sir, actually, in the lecture, it is given 1.81. So I did not understand.
Okay,
In the slide,
okay, sir, let me
so it is
just
not highest actually.
let me just open up and for the direct design method, right?
Yeah, page number 12, sir.
Okay,
Module 10, part page number 12.
okay, yes, I will go to that.
Yeah, this.
Yeah, so alpha b1, I think corresponding to that beam, I think it is 1.81. Wait, let me I'll go back and see. So 3 point 1.81. Okay,
So actually, how we have to fix it?
yeah, so and as far as my understanding goes, it has to be, we have to consider that beam where we are doing the distribution, moment
Two
distribution.
beams. In that also two beams are there, no, sir.
No sir, like only one. We have to
Middle one,
consider, this
yes,
one only.
exterior one,
No, like
exterior.
not this one. One that is along the x direction, along this direction. We have only
So
one
two
beam.
are there, no, sir. Actually, two beams are there. The interior also is there, no? Interior beam, that next one.
But this is same, no? Like,
Dimensional beam is same.
yeah. So you can, consider them as the same, because you consider this entire thing as one beam.
So in this, where we have to take, sir, actually that value, where we have to compare.
You can
Suppose it comes less than 1.9, then we have to take that one only, no?
yeah. If it is less than one, you have to take that value only.
So actually we got 2.4, 2.3,
Yeah, yeah,
2.9, that is 3.
yes, yes. So whenever it is sufficiently rigid, you will get above 1 only, but
Mhm.
in case you're getting less than 1, then you have to take that particular value.
Out of the value one comes, that we have to take, no?
Yeah, but mostly this one only, not the other
Okay.
beams, but at least for this beam you have to check the value of alpha b.
Okay, sir.
Okay, okay, thank you. So 1.0 divided by 1 plus, now L2 is 7.5, 7.5 by 6 whole square, okay, which gives us value of
Point 4.
0.
Point 4.
Yeah, 0.39. So we can say that, I'll take a different color once again. 39% is going to be resisted by the beam and 61% is going to be resisted by the slab. So now the treatment is going to be different for interior interior and the exterior slab. Okay, so the thing is, when we are considering the exterior slab, so we are not allowing the slab to take the exterior moment, so it is entirely resisted by the beam only. So if you consider the exterior slab S1, then the entire moment is resisted by the beam. On the other hand, for the span moment, it follows this distribution rule. Okay, so this would be like 61 by 2, so you can say it is 30.5%, and this is 30.5%, and this is 39%. And here also it follows this distribution rule, and also for the interior panel throughout the distribution rule follows. Okay, so this is how, once we find out the longitudinal moment, this is how, based on the proportions of the moment resistance, we are going to distribute the moment in the transverse direction as per this rule, and we are going to design the slabs according, this slab and the beam accordingly. Okay, so after this there is one small segment that is remaining. Once we have so I will just recap the steps that we have done for the direct design method. So in the direct design method, first we did the deflection check, sorry, parameter alpha b, then we did the deflection check, as per Canadian code, then we found out the static moment, then we did the longitudinal distribution, then we also did the transverse distribution. Now what remains is, we need to check the adequacy for shear. So for slabs,
So shear is only one way shear, no, sir? It is.
yes, yes, exactly. So we will check that aspect now. So when
Where-
the supporting beam or the when the slab is supported by very rigid beams, or it is supported by walls, masonry walls of very high stiffness, then we need to check it only for the one-way shear. Okay, so I will go ahead and do the calculations now. So we know that for a two-way slab, this is how the distribution happens. Like the slab is divided into two triangles and two trapeziums, and the critical section is going to occur at a distance of d from the face of the beam. Okay, so we will take a strip of unit width. Okay, and we will calculate what is the shear force that is acting at this critical section. Okay, now what would be the shear force? Shear force is given by Wu into (0.5) ln minus d. Okay, so here ln refers to the clear span, so I will just substitute all these values and find out the shear force. W is 15.75 multiplied by 0.5 into what is the clear span, that is 6000 minus 400, that is 5.6, minus d is, as we have calculated earlier, for the shortest span it is 0.155. So we get the shear force as 41.66 kilonewton. Now we need to determine the shear stress. We will determine the shear stress and then we will check what is the available shear resistance. Okay, so when the resistance is greater than the actual shear stress, then we know that the slab is safe against shear. So we have shear stress, that is tau v is equal to Vu by Bd. Okay, that is 41.66 into 10 to the power 3 divided by 1000 into 155, which gives us a value of 0.269 MPa. Okay, now I will determine the shear resistance. I think, yeah, okay, I'll just try to accommodate it over here only. Now how do we determine the shear resistance? So it is based on the IS code provisions, and it is similar to determining the shear resistance of a beam. Okay, and the shear resistance provided by concrete, tau c, depends on the grade of concrete, and the area of steel, or the percentage of steel reinforcement. Okay, now here the shear strength, let me, okay, just write it as the shear strength. Is equal to K into tau c. Okay, now Let us find out how to determine the shear strength. Okay. Okay. Okay, I will start solving it here. First I'll find out the value of AST. Okay, AST pi by 4 of 8 square into 1000 by 125, considering a spacing of 125 millimeter. So that gives me a value of how much? Pardon me, I'll just calculate quickly. .12 mm square. .12 square. Now PT is equal to 100 into AST by BD. PT is 100 into AST by BD. Okay. Which gives us a value of PT is equal to 0.26. Now let us go to the IS code and see. Pardon me, it's taking some time to open. So for this particular value, like for this particular value of PT, I'm getting the value of tau c is, I'm getting the value of tau c as 0.28 MPa. I could not pull out the IS code because it was not opening. So the value of K for slabs is always greater than 1. Okay, so the shear strength is greater than or equal to hence the slab is safe in shear. So the provided depth of the slab and the reinforcement is adequate to safeguard the slab against shear. Okay, so with that we will come to the end of this session. So we have come to the end of this session, and with this we are concluding the series of live interaction session. So if there is any feedback or comments, kindly let me know, or else we can end the session for tonight.
So effective frame method also actually I have some doubts. So 2, 3 places it is not matched when I go along with lecture.
Okay. Okay.
So I will mail it, sir. How I can do?
Yeah, okay, sir. We will. I will try to resolve, but I would suggest that if you have any doubts, then we'll be there to answer. But you can refer to the standard text like Pillai and Menon. So there also, even our example problems, they are sort of inspired from the standard texts only. So there you can go step by step and you can see how the values are coming, how the equations are being used. So I think that will help you to resolve any doubts if you have any.
Okay, sir. Go through it. If still then, if anything is there, I will
Okay.
mail it to you.
Okay. 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 Thank you so much. Okay. All the
Thank you, sir.
best.
It is a very valuable course.
Yeah.
Actually, over we are getting like this.
Yeah, thank you.
But
Actually, the two of you were very consistent right from the beginning, and I remember you sir, I think you have missed only one class, I think, but apart from that
yes,
you
sir.
have. Yeah, so yeah, it was very nice, and we can stay connected. I'm on LinkedIn, so yeah, I'd like to discuss and stay connected with you. uh, yeah, I
Sir,
really
also
enjoyed.
if this thing is added the next time in next semester, can we access it? We can register and again access it. That
uh,
choice is there or no?
yeah, it is there, sir, but the idea is like I think you have done a lot of practice. I think you have already learned the subject quite well, so I would suggest that you explore other subjects, other related subjects also.
No,
uh,
left out course I am telling you. Any left out course is there, that footings, all those things are not
okay,
completed.
that it depends next year, sir, whether sir wants
Regarding
to.
that, if we
Yeah, whether sir wants to do that and all. I know there are some special topics like shear wall and all, so that we don't know yet whether sir is planning to do that or not. That he will decide next year, and next year you can always you can see the website and see if there is any updated syllabus, so that you can yeah, if there is any updation you can join, and you can learn those aspects which were not covered this year.
Regarding is comparing with the STAT also, one person called me, sir. I mailed to you actually in NPTEL.
Yeah, yeah. Haha.
So one person called me and he proposed he will give in next week
Okay,
that
okay.
class.
Okay, okay. I'm surprised actually. Okay, I don't know. Maybe he might be one of the students from IIT Hyderabad. I don't know, because in this team, like I am from Delhi, and the rest of them are from TAs are from Hyderabad, IIT Hyderabad. So I think one of them, they might be coordinating with sir. I don't know. So
Yeah, he finalized date and time, sir. But again, that the confirmation is missing. I will call back again.
yeah, yeah,
Okay, sir.
yeah, yeah. Sure, sure. Okay.
Thank you, sir. Thank you
Okay,
very
okay.
much.
Thank you, sir. Thank you. Bye. Good night. And all the best for your exams.
Yeah, sir. It is date is not finalized yet. Actually,
I think it is 27th.
it is fixed, sir.
Yeah, yeah.
There is no
You
change.
can see the updates on the NPTEL portal.
They are giving the updates, but confirmation is not came all academic.
Okay,
Okay,
okay.
sir. They may give. Yes.
Okay, okay.
Thank you,
Thank
sir.
you.
Thank you.
Thank you so much.
Thank
Good night.
you.